My name is Jacob Douglas Kiddey, and this is my presentation on fuel cells for materials science. So to begin, what is a fuel cell? A fuel cell is a useful alternative to a battery that, unlike their competitor, does not need to be recharged. However, in order to produce electricity, fuel and heat do need to be provided externally. There are many different types of fuel cells. Some common examples are polymer electrolyte membrane fuel cells, which are also referred to as proton exchange fuel cells, direct methanol, alkaline, phosphoric acid, molten carbonate, solid oxide fuel cells, and reversible fuel cells. The focus of my presentation and project, however, will be the polymer electrolyte membrane fuel cell and the solid oxide fuel cell. So, some materials used in fuel cells. The electrolyte for an SOFC is a ceramic, and the most common ceramic used is lanthanum chromite. The anodes are commonly made of nickel, ruthenium, copper, and sometimes platinum. Common cathodic materials are perovskite and lanthanum strontium manganite. The electrolyte for a proton exchange fuel cell is a polymer. A commonly used polymer for them would be polybenzimidazole. The electrodes are carbon-based with platinum or a different noble metal being infused within them to act as a catalyst. The solid oxide fuel cell, which is one of the focuses of my project, is also one of the most common used fuel cells along with the proton exchange fuel cell. It operates via a hard, non-porous ceramic in the center as the electrolyte, surrounded by an anode and a cathode on either side. On the anode side, natural gas that has gone through a reforming process and will enter the cell is steam. While on the cathode side, oxygen will enter. Oxygen will then combine with the free electrons, creating oxide ions at the side of the cathode. These oxide ions will then travel through the ceramic electrolyte to the anode. And at the anode, these oxide ions will react with the hydrogen and the carbon monoxide, forming water and carbon dioxide respectively. These free electrons will then travel back to the cathode through an external circuit, which is how the fuel cell will produce electricity. They are observed to be around 60% efficient, operate at incredibly high temperatures, sometimes getting as high as 1,000 degrees Celsius. A benefit, however, is that they do not use precious metal catalysts and are able to use quite a high variety of fuels because they can reform fuels internally due to their high temperatures. Some challenges that are faced with solid oxide fuel cells is they have a slow startup due to the high temperatures they require to operate. The cell itself requires significant thermal shielding to retain the heat and protect human operators, and the metals in general just need to be durable due to the intense conditions. The outlook for the SOFC, scientists are working on producing an SOFC that can operate at lower temperatures. Some have been tried operating as low as 700 degrees Celsius, which can just broaden the use of different metals in order to operate the SOFCs and overall make them safer. However, these lower temperature solid oxide fuel cells have been unable to replicate the efficiency and power generation that the higher temperature ones have been able to produce. The polymer electrolyte fuel cell is also commonly referred to as the proton exchange fuel cell, as previously stated, and is another very common type of fuel cell that is used. It operates via many layers of the following materials. A polymeric electrolyte, which is then bonded on both sides to an electrode. Most commonly, this electrode is made of a porous carbon with a noble metal like platinum incorporated throughout the carbon. These membranes I described are called MEAs, or membrane electrode assemblies, and they are separated by bipolar plates and stacked on one another to make the cell. The cell itself works in a similar way to the SOFC, where air enters the cathode side, and fuel, for this cell, the fuel of choice is pure hydrogen, enters the anode side. And the oxide ion traverse through the electrolyte, and the free electrons travel through an electrical circuit back to the cathode, which is what generates electricity within the cell. These polymer electrolyte fuel cells have been observed to be roughly 40% efficient in the best case scenario. Operating conditions, however, are only around 80 degrees Celsius, which makes them much more useful for transportation and things like that, where they need to be operated in different machinery or operated by people. Platinum is typically used, or a platinum alloy catalyst. They can operate with only hydrogen and oxygen from the air and are typically fueled with pure hydrogen from storage tanks or reformers. Some challenges that you face when using a polymer electrolyte fuel cell is that they require a noble metal catalyst, which is susceptible to carbon monoxide poisoning, which is where the carbon monoxide reduces the catalyst activity by blocking active catalyst sites, which would usually be available for oxygen, for hydrogen co-absorption and dissociation, causing the need for additional reactor that will reduce the amount of carbon monoxide in the fuel gas if the fuel is being derived from hydrocarbon. Which just poses logistical issues of either finding pure hydrogen storage tanks or, as previously mentioned, just finding separate reactors to reduce the amount of carbon monoxide. The outlook for the PEMFC seems to rely on the improvement of hydrogen fuel infrastructure and improved efficiency of the cell itself, as it is considerably outclassed by traditional lithium-ion batteries, which are used for the transportation industry currently. This is my Simulink model for a PEMFC fuel cell, although it could easily represent a SOFC model given different flow rate and temperature parameters. This particular model is only being observed at 24% stack efficiency, as you can see on the blue line in the given graph, marginally lower than the greatest performing PEMFCs that have been displayed and constructed in the past years. That's kind of to be expected with this design, because I'm an undergraduate. I don't exactly know how they were able to achieve such a high stack efficiency on their fuel cell. And with the tools accessible to me, I can't exactly change the metals being used. This is just in industry standard observations that you see in a fuel cell. Overall, I hope this model can convey a clear picture of how a fuel cell can take hydrogen and air and convert it into electricity. I believe the advancement of this technology is imperative to the advent of clean energy in the future and replacing things like batteries, traditional lithium-ion batteries that you see in cars and whatnot, with different hydrogen fuel cells that produce less waste and overall use cleaner fuels in order to power different industries like the automotive. These are the references I used in order to gather this information for the presentation. That is all.